warahmatullahi wabarakatuh. Hi, and welcome back to our video lecture for the next discussion on induction machines. So last week we have looked into the basic operating principle of induction machines. We have discussed about the rotating magnetic field. We have discussed about what do we define as slip that produce basically that is basically the mechanism of torque production in induction machine. And we have also looked at the operating torque speed characteristic of induction machine, like the curve of torque versus speed of induction machine. So today, following that discussion, we are going to continue into discussion on how do we start that machine, the problem related to starting an induction machine. So we'll discuss about what we call as starting resistor, and then we look into the mode of operating as a generator, and we'll briefly discuss about equivalent circuit, which is basically a method to analyze the electromechanical parameters or performances of the induction machine using circuit analysis. So let's begin with efficiency. So the efficiency of an induction machine is very much related to the slip, to the ratio, to the value of slip. Why? Because we know that if the machine is operating with the rotor is very close to the synchronous speed and s, then it means the machine is very efficient, where it can pull the load very easily. To calculate that efficiency, of course, if you have your hand on the if you are able to quantify the mechanical output and the electrical input of the rotor, then you would be able to calculate the efficiency, of course. But if you don't have that, then what we can do is basically just by looking at the slip, and it is simply by the formula is simply is the inverse of the slip, or 1 minus slip. Okay, so if you want to know the efficiency of induction machine, the efficiency of the rotor pipe, it is equals to 1 minus the slip. Okay, so from there, the issue that we are going to discuss now is related to operating the machine, especially when we want to start the machine. So we have seen last week the curve of the curve of torque versus speed and induction machine. So the curve is like this curve. So here I'll explain later. We have multiple curves, but if we have a machine with, for example, a cage rotor, what's going to happen is that we are not going to be able to modify the rotor resistance. So we know the other option is to have a machine, wounded machine, where it is connected to slip rings, and then it's connected to a certain a variable resistance, where we can modify the value of the resistance of the rotor of the machine. But if we don't have the ability to modify the value of the resistance, what's going to happen is that we are going to have only one curve like this. So at resistance equals to R, resistance of the rotor, and we have seen that at starting, when we start the machine, what's going to happen is that we're going to fall at this point of torque, right? So the slip is at maximum. We are going to fall at the point of starting torque. We know that the machine is going to be able to deliver more torque later if we can go to if we are able to go to the speed that is closer to the synchronous speed, where the slip is 0. Okay, so to understand the problematic, so let's imagine we have a load. So if a load is lower than the starting load, then, so for example, if the load is placed over here, somewhere over here, and I'm gonna take a pen so that'll be much better. So if I have a load that is located over here, which is much lower than the starting load, starting torque. I'm sorry, starting torque. So what's going to happen as we start the machine, and the machine is going to be able, from slip, maximum slip, is going to be able to go, following this curve, to go back to the position where the slip is minimum, right? Okay, so that would be no problem if the load torque is very, very small. But what happens if our load torque is at a certain level that is higher than the starting torque? So imagine if we have a load torque or resistive torque at this value. So what's going to happen is that the machine is not going to be able to start because the load torque is much higher in comparison to the starting torque. So what we need to do is basically to increase the starting torque. So the starting torque that was over here, we need to increase it to a level that is much higher than our resistive torque. So in order to do so, an interesting behavior of induction machine is that if we increase the value of the resistance of the rotor, then the curve will the torque versus speed curve will shift in form. The form will shift a bit. So what's going to happen is that the starting torque will increase. So if you add your resistance equals to 4 times the initial resistor, the curve is going to be this curve. If you add to 6 times resistor, the curve is going to be this curve. And you add more, and if you add more and more, it could be it could end at starting torque equals to maximum torque. But the curve now is going to be like this. Okay. So if you have a much higher rotor resistor, the starting torque will be much higher, and the form of the torque versus speed curve will change. So what's going to happen is that for starting the machine, we manipulate the value of the resistance of the rotor in order to be able to increase the resistive torque. So higher rotor resistance give a higher starting torque, right? Okay. So if it is, for example, in this solution over here, we have to increase the resistor torque to a certain value where the starting torque is higher than the resistive load torque. And then once it has started, then you can gradually decrease when it has started and it goes to the synchronous speed or this synchronous speed at a very low speed, then you can reduce back the resistance of the rotor, reduce back to this level so that the operating point will remain here. Okay, so to start, you increase the resistor. Once it has started and the sleep goes from 0 to this point, you can redraw back the resistor, reduce the resistor back, so as to not consume too much energy. So that's the purpose of using the structure with slip rings. So for a machine that was designed for a specific load, you can basically choose a machine where the starting torque is much higher than the load. But for a machine that's going to be used for for different starting load, then it is better to have this control on the starting torque with the integration of slip rings and brushes, with the integration of variable rotor resistor. Okay, so now we have seen most of the theoretical background. Not theoretical background. We have seen on the generalities of the operating principle of machine in normal mode, in what we call as motoring mode. So if you look at this graph over here, torque versus speed. At the bottom we have, as usual, the axis for the sleep, for sleep. So our curve that we have discussed just now is basically this part of the curve over here. Is the curve when the motor is functioning in motor mode or motoring. So it is when you have your sleep from 1, so it's positive sleep from 1 to 0. So as we can see in the graph, there is other possibility of sleep where you can have a negative sleep. So what does it mean by negative sleep? Sleep is that when the sleep when the rotor is rotating faster than the synchronous speed. So that is when you have negative sleep. It means the sleep is not because the rotor is slower than the synchronous speed, but now it is because the synchronous speed is slower than the rotor speed. It means you have a certain speed of synchronous speed, but your rotor is rotating faster than that synchronous speed. What does it mean? It means basically it means that your rotor is being trained by an external forces so that it rotates faster than the synchronous speed. So let's look into detail of these other modes other than motoring. So first one, let's imagine if S larger than 1. So S or sleep larger than 1, it means we are going into this side of the curve. Okay, this side of the curve. Sleeps larger than 1 means that the rotor runs backwards. So if you remember the equation for slip, the ratio is it is basically the synchronous speed minus the rotor speed divided by synchronous speed, right? So how would you get this value larger than 1? You could only get a value larger than 1. I'll write the equation to make it clear. So we remember the equation for slip is S equals to synchronous speed minus the rotor speed divided by ns, right? So the first case is when s is larger than 1. How could we have s larger than 1? We know that synchronous speed is fixed due to the frequency, so it cannot be much larger. So in order to have it larger than 1, and we know that n over here is between 0 and synchronous speed. If we want to have s larger than 1, it means n needs to be negative, right? N needs to be negative. So what does it mean n negative? It means that the rotor is rotating in the opposite direction. So that's why we say the rotor is running in backwards direction. Rotor runs backwards. That's when we have s larger than 1. So if the rotor runs backward, which is the opposite direction of the field, while the torque remains positive. Why the torque remains positive? Because there is still slip, all right, but the slip getting larger, so the torque is still in the same direction. It's just the rotor is now being rotated in the opposite direction. So what's going to happen is that due to the torque, the rotor will slow down, right? And then it will change direction and accelerate back to the synchronous speed. So this is the condition where, for example, if you are at 0 over here, at a rotor speed equals to 0, and then we have an s at a certain value. So for example, if it is 3000 rpm for a 2 poles machine, at 3000 rpm, so you have a certain induced current, but you have a something that is training the machine to rotate in the opposite direction. So if you are rotating in the opposite direction over here like this, what's going to happen is that you have a slip larger than 1, but the torque is going to increase. Okay, you can see that the torque is increasing, right? The torque is increasing. It increases, and it is going to continuously increase because the slip is very large. So if you stop the force that's moving the rotor in the opposite direction, what's going to happen is that the torque will bring back the machine in this direction, and then it goes back into synchronous speed. So that's what happened in this area. So there is always torque that will bring back the speed onto the positive direction. So that's why we call this operating mode, when you have s larger than 1, as braking operation. So you can brake a machine, you can brake a shaft by of an induction machine by applying a rotating magnetic field in the opposite direction. So that is braking. Another operation is when you have your slip, as I mentioned just now, in the opposite direction over here, where you have your slip smaller than 1. So how do you have a slip smaller than 1? You have a slip smaller than 1. If you look into the equation, you need n to be larger than ns. So it means that your rotor speed is much larger than the synchronous speed. So that is exactly the condition when you have when you are training when there is an external force that is driving your rotor. For example, in a wind turbine, when you are feeding a certain frequency to your stator, but there is an external force, basically the wind that's turning your turbine blades, and that's turning your rotor at a speed that is much larger than the synchronous speed. In that case, what's going to happen is that your torque is going to be in negative direction. So what does it mean having a torque in negative direction, opposite direction? It means that if your load is capable to supply torque to maintain the rotation, so if the load over here, the load means the turbine, if it is able to always maintain that rotation, to maintain that negative torque, what's going to happen is that that mechanical energy is going to be converted back into electricity to the supply. now we are going to discuss about the equivalent circuit. So what is an equivalent circuit? The purpose of equivalent circuit is basically to represent all the parameters of the induction machine, electrical and mechanical, electromechanical, in terms of electric circuit. So that you can do an analysis like in electric circuit to be able to deduce different parameters of the machine, such as how much current does it pulls, what is the line current for a certain load, what is the slip right now as it functions, what is the efficiency, and so on and so forth. Right. So to do that, the equivalent circuit that we're going to study is, of course, an equivalent circuit that has certain impedance components, especially inductors, right? So it is not only a resistive circuit with only resistor. It will be involving, of course, inductor, because an electrical machine, is basically just a coil, a combination of coils, so they have inductance and therefore impedance. So what is impedance? Impedance is basically the combination of resistance and reactance, right? Resistance and reactance. So it is basically something that you have seen in basic electrical principle in first or second year. So the Ohm law applies not only on resistor, but it also applies on the impedance. So for example, if you have only resistor, then your circuit will have in terms of impedance only resistor. But if your circuit have inductor has a certain reactance, which basically modify the Ohm law. Well, not modify the Ohm law, but modify the relationship. So what is Ohm law? Ohm law is the relationship between voltage and current, right? So if your circuit is resistive, the relation between voltage and current, there is only R. So V or U equals to Ri. But if your circuit has more than resistor, inductor, and capacitor, then it's not simply U equals to Ri, it's U equals to Zi, and Z is the impedance. So the impedance, you need to include the component of reactance if you have inductor and capacitor. So this is basically the generic, the formula of calculating the impedance of each component, resistor, inductor, and capacitor, that you have learned previously. So in our circuit, we will have inductor, and the reactance of inductor is omega L, and the impedance is j omega L. So in electrical machine, you will have resistor because the coil have a certain resistance. So it is a combination of both R and j omega L. Okay, so the omega L is what we call inductance, reactance, and L is the inductance of the coil. So we can see that it is proportional to the frequency of the current supply, and it is proportional to the inductance of the coil. So the faster we go, if you have a higher frequency, then the higher will be the impedance. Okay, so this is just the basic thing that you have already known. So if you are applying AC current, then the inductor becomes what we call as a self-inductance. So it stores a certain energy, and it becomes a reactance, where what's going to happen is that it's going to, if you look at the phasor diagram, it is going to first create back EMF in itself. So if you are supplying with a voltage V that is sinusoidal over here, we are going to observe a back EMF created by the coil. So the back EMF is in opposite direction, it is phase shifted, it is in opposite direction, right? You do understand that if you draw the equivalent circuit in, for example, in armature, we know that the voltage supply is one direction, but the back EMF in the opposite direction. And then therefore you have a certain current generated due to the back EMF. And what is the value of current? The value of current, the relation between two, is basically the impedance, right? So the amplitude difference is due to the impedance, and it is not just the amplitude. There is also what we call as phase shift. We can see that the peak of the current is not in phase with the peak of the voltage. Why? Because we have a certain reactance, right? So if we draw a phasor diagram, how much delay, how much phase shift do we have? Basically, the current is always lagging 90 degrees behind the voltage. So we can see the peak of the current is 90 degrees behind the peak of the voltage. And if you want to write the equation of the current, current IL equals to I max sine omega t minus 90 degree. So 90 degree is basically the phase shift behind the voltage. So if you have an RL circuit, right? If you have an RL circuit, then what's going to happen is that your current is not going to be in phase. So it is a vector. It's going to be a vector like this. So there is a component of a VR voltage. If you have a current, then the voltage will be like this. It's not going to be in line with your current. The voltage, there is a component VR that is due to the resistor, but there is a component VL which is 90 degree delay lagging. So in axis J, VL, the combination of both create this voltage that has a certain angle theta, which we call as power factor. Right? So this is just a revision. So this is what we call voltage triangle, a component of voltage that is created due to the resistor. So it's a relationship between current and resistor. There is a component that's perpendicular to it due to the basically reactance. So in this case, it's only inductor. This is what we call as a reactive part, and then both of them create the total sum of those vectors. Basically, the real voltage. It has a lag of phi behind the voltage supplied. Okay, so the lag is not 90 degree. 90 degree is only if the circuit is purely inductive. But if you have resistor, then it will be less than 90 degree. It has a certain angle of combination of both. And in terms of power, if you want to calculate the power, then you have, of course, the triangle of power as well. You have real power, which is due to the resistor, so Ri square. The power over here, the real power P, or Vi cos phi. So if you have this power, what we call as apparent power, Vi cos phi is the real power. It's also Ri square. You have also the reactive power. Reactive power is Q, is Vi sin phi. So sine is the y-axis quantity, and then the power the power that it is absorbing is basically the apparent power, S. So S is just V multiplied by I. This is the power S. So the apparent power in a volt ampere is basically this power, apparent power. So it is real power square plus a reactive power square root. So this is the apparent power. So the apparent power is larger than the real power. The real power that will produce the mechanical output, right? So either in heat or in mechanical output is the real power. The reactive power is basically the magnetizing power, and apparent power is power that is absorbed by the input. So if the circuit is very reactive, the Q magnetizing power is too much, then we will need a lot of energy in input in order to produce certain real power. So usually what's going to happen is that the real power P is much higher in comparison to the magnetizing power by the stator. So by now you understand that the operating principle of an induction machine is relying on the principle of induced current. So in stator you have an AC current, and the rotor is basically it's a passive component. It's not supplied with electricity. It's just put in the middle, and the magnetic flux goes across it, and the variation of magnetic flux inside the rotor will create the induced current. So this principle of operation is exactly the same as what we have in a transformer. So if you remember in what we have learned in first year or second year, the operating principle of a transformer is that you will have a primary, and then you have a secondary. The primary will have an AC current circulating to it, right? And then the variation of that AC current inside the core will basically create an induced current inside the secondary coil. So it is exactly the same thing, and well, that is why the induction machine is also sometimes called as a rotating transformer. So you may find the terms as rotating transformer. It basically means induction machine. So because it includes the same part, the primary in transformer is basically we can consider it as the stator field, while the secondary is our rotor cage or winding, right? So the stator is primary where the input AC voltage is applied. The secondary or the rotor cage and the rotor winding is where the added flux or the flux wave just now creates the induced current in it. So a circuit can therefore represent an electrical behavior of induction machine, just like a transformer. So let's go to a transformer model first. We have learned this in AC analysis and application of transformer. So in a transformer model, we may create an equivalent circuit that looks like this. So we have on the left side the primary, on the right side the secondary. We have the line voltage, the phase voltage that we are supplying over here. And then on the right hand side, we have basically the load of the circuit that we call as Z2 over here. So there are several components in the circuit. The first one would be the thing that is noted as R1 and R2 in red are basically the winding resistance. So you have the primary winding and you have the secondary winding resistor R1 and R2. And then you have X1 and X2. What is X1 and X2? X1 and X2 is basically representing the energy absorbed by inductor. But in this case, it's not the inductor, the real inductor that is magnetizing the circuit of the motor or the transformer. It is the leakage inductance. So represented as X1 and X2. So there is leakage inductor, very small amount of leakage inductor in primary and a small leakage amount of inductor in the secondary. So the leakage, as we discussed in first chapter, leakage is due to, for example, a certain form or due to the air gap surface. There might be some fringes of flux that leak. So it could be presented as S1 and S2 over here. And then the thing that is in parallel over here is the magnetizing part. Right? It is the magnetizing part of the circuit where we have RC. RC is the core losses. Core losses is the losses that is due to the frequency. So that is the nature of material. If you have an AC current in it, it will create what we call as eddy current and what we call as hysteresis losses. So it's related to the material characteristic of the core material. So the core of your machine. If you have an AC current through it, there is this kind of losses. So this is quantified by the RC and XM of the magnetizing circuit. Okay, so this is basically the model of a transformer, and it can be simplified because we don't like to have two separate circuit like this. It's very hard to analyze, but we know that in between the two circuit we have the ratio of N1 and N2, which is the ratio of the transformer, right? The amplification or the transformer ratio. So in order to make it simpler, what we can do is to bring the secondary part into the primary part so that it can become one single circuit like this. So the secondary parameters, which are the load resistor, the resistors and the inductors of leakage, can be brought to the primary by using just the ratio. So for example, if you bring the load Z2 to become now Z prime 2 in the primary part, you just multiply it by N1 over N2 squared. So this is the ratio how you do to bring the secondary part into the primary part. So just now that was basically the equation, I mean the equivalent circuit for a transformer. Now applied to induction machine, it is basically exactly the same thing, where you have the same core losses RC and XM, where you have the rotor. It was secondary for transformer, but now it's rotor leakage inductor for for the rotor and the resistance of the rotor. You have the resistance of the stator and then the leakage flux for the stator. So you have the exact same model, but the only difference is basically in terms of the load resistor. So the load resistor is not an electrical resistor. It is a resistor that represents an electromechanical load. So the electromechanical load is basically in relation to the slip as well. So the equation is like this. So it's a certain value of resistor multiplied by 1 minus S over S. So what are the analysis that we can do? So in order to see what kind of analysis that we can do, let's try an example. So we are considering this now that this equivalent circuit has a certain parametric value like this. So for example, the R1 equals to 0.2, X1 is J1, X prime 2 is J1 as well. The rotor resistor R prime 2 is 0.3, and then we have what else do we have? We have the full load speed of 1728 RPM. So this one R prime 2 is 0.3. And then here basically it is the calculation of 1 minus S over S. So 1 minus S over S, now it shows that the slip is 0.04, leading to a total load resistor of 7.2. But first, how do we find this load? Others are given, the value of resistor, inductor, and inductors are given, and we have the input voltage of course AC voltage of 440 volts. So we can imagine, for example, if it could be 50 Hertz or 60 Hertz. It's not mentioned for the moment here. The first thing that we could do is basically to calculate the slip. So how do we get this slip? It says that the machine is operating at 1728 RPM. We may calculate slip, therefore, if we know the frequency, but now we don't know frequency. The question asks us to calculate three things. The first thing is the line current IS. So what is line current IS? Line current is what we have here. I1 is not the line current, it is the phase current. Line current is basically, if you remember in AC analysis, line current is basically just the phase current multiplied by square root of 3. So what we need to do is to find basically the phase current first, output power, so we need to calculate the output power, and then the efficiency. So let's start. Considering all these parameters, the first thing that we need to do is to calculate, of course, the synchronous speed. It is given now here that the power supply is basically, the machine is a 4-pole machine, but now it is equivalent circuit for one phase. 4-pole machine is a 60 Hertz frequency. 60 Hertz frequency. So from this frequency, we know what the synchronous speed is, right? So with a frequency of 60 Hertz, we use the formula that we've learned just now. The synchronous speed is 120 F divided by P, the number of poles. So number of pole is 4, frequency is 60. You do the calculation, you get the synchronous speed equals to 1800 RPM. Okay, now an observation. Synchronous speed is at 1800 RPM, but the full load speed, the machine when it's operating the load, the machine is basically rotating at 1728 RPM. So there is a certain reduction in terms of speed in comparison to the synchronous speed. Therefore, we can calculate the slip. So what is the slip? Slip is synchronous speed minus the rotor speed divided by synchronous speed. So 1800 divided minus 1728 divided by 1800. Therefore, we got 0.04. So that's what have been entered over here, 0.04. It is the value of slip, knowing that the speed at full load is 1728 RPM in comparison to the synchronous speed of 1800 RPM. So now we have the slip. If we have the slip, therefore we can calculate the electromechanical resistance. Electromechanical resistance is R prime 2 multiplied by 1 minus S divided by S. It is already calculated over here. So the resistance of electromechanical load is 7.2 ohm. 7.2 ohm. Now we know the resistance, right? So this is the resistance that was missing. We know the resistance. We know all the value of the parameters. Therefore, we can do a circuit analysis now. So to do the circuit analysis is basically just application of Ohm law in order to, at the end, remember the objective is to find the phase current I1 to finally multiply it by square root of 3 to get the line current. To get the phase current. So if we look at this circuit over here, we need to first identify the impedance of each branch. We can see that there is one branch here where I1 come in, and then it is separated at this node into two branch, one branch of IM and another branch of I prime 2, right? So the current I1 separated into two branch IM and I2. Therefore, what we can do is basically this reactance, we can calculate the reactance of this branch. We can calculate this reactance of this branch as well, and so this branch is basically including J1, 0.3 and this resistor. So this is another branch, and we can see that this branch and this branch, so the rotor branch and the air gap branch or magnetizing branch, are basically in parallel, right? So we can do the calculation in parallel, and then therefore we can deduce what is the current in I1. So let's have a look at it. So first, identify the impedance. Impedance of rotor is basically J1 plus 0.3 plus 7.2. So we get J1 plus 0.3 plus 7.2. We get 7.5. So here we get the resistive part 0.5 and the reactance part is J.1. So or in angular notation, you can also, because this is the notation in complex number, the notation in angular notation is 7.57 with an angle of 7.6 degree. Okay, and then what is the impedance of the magnetizing part? The impedance of magnetizing part is simply 250 plus J40. So here there's a mistake over here, or mistake in the value. So it should be, for example, here in the value it should be the resistor over here is 6.25 and the reactance over here is J39. So this is a wrong value that I put on the schematic diagram, on the circuit diagram. Okay, so this is ZR, the impedance for the rotor branch. This is ZM, the impedance for the magnetizing or air gap branch. So both of them are in parallel. So if you do the calculation in parallel, if you find the equivalent, do the parallel of both, you will find that is equal to this particular impedance in parallel. So added to it, the both resistor in parallel, it is in series with the stator part. So if you add the already parallelized equivalent parallel resistor to the stator impedance, that impedance is 0.2 plus J1, added to it, you will get the final total motor impedance. So this is the total motor impedance. So all the impedance over here have been reduced to only one impedance. Therefore, you can use Ohm law to calculate the current. So I1 phase current is the voltage. So the voltage is 440 volts phase 0 because it is the reference. The voltage is the reference 0 divided by the impedance, and the impedance is 7.61 with an angle of 24.2. And if you do the division, you get 57.82 with an angle of minus 24.2 degree amps. So this is the AC current of the phase current I1. So in order to find the line current, what is the line current? So the phase is, of course, we are not interested in the phase, because the phase in line or in phase current or in line current are going to be the same. But the thing that's going to be different is basically the amplitude of the current. So the amplitude of the current in phase current I1 is 57.82. Therefore, in line current for phase 1, it is square root of 3 multiplied by I1. So square root of 3 multiplied by 57.7, you get 100 amps. So the line current that is pulled by the motor as it operates this load is equals to 100 amp. So the load that induce a slip of 0.4 will pull a current in this machine in line current of 100 amp. So output power, how do you calculate output power? Output power is basically, output power is the power consumed by the load resistor. So it's I prime I second I2 prime square multiplied by R.
because the power consumed is Ri square, right? So it's the load resistance R multiplied by I prime square. So how do we get I prime square? We already know I1. We know the impedance of this branch and the impedance of all this branch. So you can do the current divider method to find I prime 2. So I prime 2 square multiplied by R will give you the output power. So I'll let you do it on your own. Please try it on your own as well. And efficiency, therefore, what is efficiency? Efficiency is output power divided by the input power. So output power, we have got it just now. What is the input power? Input power is the input current I1 multiplied by the voltage V1, right? So that's all that we need to learn in this week. So if you look at the operating mode of generator, we have looked also at the equivalent circuit that allow us to analyze basically the current, output power, efficiency due to a certain load that is induced by the sleep. Okay, so thank you very much. That's all on the second part part of the induction machine. And until I'll see you again in the next lecture, thank you. Goodbye.